Thank you, Peter. First of all, I'll just say it's a pleasure to be here today in Ireland. Today I'll be giving a talk about embodied carbon in construction. So Jane's just given a nice overview of life cycle assessment, which is broader than just carbon. Today I'll be talking about embodied carbon and a bit about embodied energy. So I've got an introduction, then I introduce carbon footprinting as a concept, a few slides about background, a few tips on what you can do to reduce embodied carbon in buildings, and then I'm talking about an overview of a piece of work that we delivered jointly with Davis Langdon for the Sustainable Energy Authority of Ireland on embodied carbon. And this project has improved the embodied carbon data for Irish building materials and products. If we have time, which we might not do, I have a few slides on supply chain carbon. So, introduction. I'm sure you've all seen this before, but sustainable development and sustainability. Back in 2000, Sarah Parkins determined that there was over 200 definitions of sustainability. I suspect there's a lot more nowadays. But the most populous one is probably meeting the needs of the present without compromising the ability of future generations to meet their own needs. So what this says is we need to hand down the planet to our children, our grandchildren in a sustainable manner. And true sustainability is a balance of social, environmental, and economic factors in true harmony. Quite often nowadays, people talk about sustainability just in terms of the environment and use them almost interchangeably, which is inaccurate. Also, people are quite guilty of talking about carbon as sustainability, which it's not. It's the true balance of all three, and you've probably seen the sustainability Venn diagram before, which balances the three factors together. I just like to think about this when I'm making decisions on the work that I'm doing. But today I am going to concentrate on carbon, which although is not a full sustainability, is an important part of sustainability. I'm sure you've all seen graphs like this. This is just the world's GHG emissions from fossil fuels. Back from 1750, this only goes up to, I can't read the graph, 2000 and something. And I'm sure you've all seen the trends like this before, but what surprises me that within the lifetime of anyone within this room, the rapid increase is astronomical. So this is about the end of the Second World War, and the rate of increase is naturally, you don't need to be an expert to see that's unsustainable. So something needs to be done, and the rate of increase is going up even further. So what is being done? Well, there are certain mechanisms, such as the Kyoto Protocol, which I've got one slide on here. One mechanism which looks to try and tackle, or one of the first mechanisms, international agreements, that looks to try and tackle the world's CO2 emissions. This is now 1 year out of date, but it still has the same general conclusion that from 1990 to 2008, the world's emissions went up 40%. The last 18 years, the world's emissions went up 40%. They need to go down, not up. You break this down, the Kyoto parties with a target went down 9%, just over 9% in the same period. On paper, that looks really good, because the target was just 4.5%. So they've exceeded that by twice. But you go and break that down further, and Europe Europe is, emissions went up 2% over this period. Every country in Europe's got a very different profile. North America, which is just Canada, went up 27%. The Pacific, 17%, which includes Australia and Japan. So these are all big increases from all the big industrialized countries. Where has this minus 9% come from? Well, Europe doesn't include what's called the economies in transition. And these are countries such as the Czech Republic, Hungary, Poland, Russia, Ukraine, ex-Soviet, ex-Eastern Bloc countries. And they've had a 32% reduction in their CO2 emissions over this period. But that's not come from their efforts to reduce carbon. That's come from the collapse of their industrial economies after the collapse of the Soviet Union. So this makes Kyoto look a success, but when you dig down deeper, not enough is happening. So we need to do more. And what can we do? Well, you can bring decisions into everything that we do. And one of the tools of doing this is carbon footprinting, and in construction, embodied carbon. Construction is a key sector, or buildings and construction. Of most of the westernized economies, buildings and construction consume about half of the GHG emissions from most of the industrialized countries. It needs to be on board. So what is a carbon footprint? And in fact, what is embodied carbon? Well, when you talk about a material or a product that can be used interchangeably, embodied carbon is a carbon footprint of a material, any material. Carbon footprint can also be used for the carbon to operate this building, the lighting, the heating, etc. And where it comes from is an early concept known as ecological footprinting, which is what this diagram here tries to represent. And this tries to break down the different areas of land you need to sustain your activity, or indeed the whole of Ireland's economy. So this representation breaks it down into different types of land. You've got forest, farming, energy, land to live on, water resources, etc. And this is a spatial indicator, which is measured in hectares. Now, I'm sure you've all seen reports from the WWF, which says we need 3.5 planets to sustain our activities, or 12 planets by a certain date. This is where this concept comes from. But nowadays, carbon footprint is not a spatial indicator. It's more about, talked about in terms of tons of CO2, tons of greenhouse gas emissions. And these mainly come from the burning of fossil fuels, which are typically most significant. But it's not the only source of carbon. There's also chemical reactions when you make a lot of materials. So cement is the most obvious example in construction. About half of the carbon emissions from making cement come from a chemical reaction in the kiln when you're firing the material. A lot of other materials have these kind of chemical reactions, including steels, bricks, ceramics, glass, etc., but on a much reduced scale. But tracking embodied carbon is not just a case of I've got 1 barrel of oil and that's how much carbon, when you burn it, that's how much carbon is accounted for embodied carbon. It's a true journey tracing things back to the cradle, so the cradle being the earth. So it counts all the activities, right from extracting things from the ground, that could be extracting a fuel from the ground, or indeed extracting an ore from the ground to make, say, steel, aluminium, or coal, for example. Adding in transport to, for example, any refining that needs to take place. Then there's even more transport. Then onto factories, or indeed factories, various fabrication or assembly operations. These factories consume more oil, gas, electricity, etc. And then, let's say you have a product. Then onwards to the construction site. You have packaging, you have distribution, even more transport and storage in warehouses, and then it goes to construction site. You'll notice I've mentioned transport quite a lot. You'll see from Jane's graph earlier at the slide of her presentation that transport was not as significant as the materials itself. So although it is important, people are getting away from the whole concept of what used to be popular food miles, in that the embodied carbon to make a material is generally more significant than the carbon to transport the material. So you can't just source materials locally, I'm afraid, without considering how the other sustainability credentials of manufacturing that product. There might be a more environmentally friendly manufacturer a slightly longer distance away. I also have a slide later on that it very much depends how you transport a product and not just the simple miles. Then the construction site is actually quite important because you need to power the site. You've got porter cabin, you've got generators, you've got all sorts of equipment and machinery for assembly activities, and indeed construction waste. People often forget about construction waste. There's some very good waste rate factors from RAP in the UK, or BRE have some waste data as well. Because to make a brick wall, you need more than 1 square metre of bricks worth to make that wall, because there's a lot of wastage. Contractors will over-order bricks and then they'll be disposed of afterwards, or they get chopped in half and the other half chucked away. In fact, the average waste rate, according to RAP for a brick, is for every brick in the wall, an extra 25% gets bought and never used, as typical. These can generally be halved, but the embodied carbon of waste can be quite significant, and then there's the waste management activities as well. Capturing all of this gives the cradle to site embodied carbon. Representing on the one diagram, you have the extraction raw materials at the top, transport activities, manufacture, transport to site, build. Then what? The building goes through its operation, and then end of life. Whole life carbon captures all these activities, and in fact, a slice of the operation in terms of maintenance and materials. So embodied or whole life carbon captures all of these components, anything related to the materials rather than the operation of a building. To put some crude numbers, the embodied carbon of a lot of houses is about 500 kilograms of CO2 per square meter that you're constructing of a house. Now, that's roughly 22 years of operational carbon, excluding the appliances of the house, such as I don't know, IT equipment, fridges, etc. But you're not counting the embodied carbon of that in the calculations, so that's quite fair. Offices has a huge variation, so more like they can be down to similar to a house, or they could be up to about a ton of CO2 per square meter. The high end's more typical for high-rise office buildings. And this is quite often 25–30% of the whole life carbon of that building. That's already a big chunk of carbon. And for me, what's significant here is that embodied carbon doesn't get much attention for reduction, and you can very easily reduce the embodied carbon of most construction assets or buildings by 10%, 20% with cost-effective measures. And that's a good opportunity to reduce carbon there. If you don't take that opportunity and you build the building, you've released a huge amount of carbon in a very short time frame, let's say a year, 2 years, etc. And the opportunity to reduce is already gone. It's too late. You've released it, you've wasted it, you've not taken the opportunity to reduce. But if you mess up the operational carbon of a building, although it's not ideal, you can still go in and retrofit it and correct it. You can still use cleaner electricity sources or cleaner heating sources. It's not ideal, but you still have an opportunity to change. Therefore, for me, it's already 20–35% of the whole life carbon of a lot of offices. But actually, this doesn't consider any improvement in the operational performance of an office. And they consume electricity, which is getting cleaner all the time in the future as we increase the amount of renewables. We reduce reliance on coal, or carbon capture and storage comes into the future. So for me, embodied carbon, it's a single large upfront release that should get more attention. This is just a rhetorical question, just to make you think. Which is lower embodied carbon, timber or steel? Well, most people's natural reaction is timber, but I'm afraid it depends. It's not as simple as that. What if there's 1,000 kilograms of timber, let's say unsustainably sourced timber, but only 1 kilogram of steel? I know that's an unrealistic balance, but to provide the set function, you need to consider a wider number of factors. You need to consider how much mass of each material you need. You need to consider the lifetime durability to provide exactly the same function. So it's not as simple as timber is the answer, steel is the answer, etc. It's about the application. How am I doing for time? I've got a few slides on reducing embodied carbon. I've got some on tips of... Okay, on time. Tips, things to include. I'm going to skip this and this. Talking about designing a building, you have the greatest opportunity to influence a building the earlier in the design stage that you get in there. So before it's even been designed or commissioned, you have the greatest ability to influence because you're setting the brief. The later in the design stage, when it's all been fixed and all the materials being procured, you have less ability to influence. So there's a huge potential for design to get in there early on. And this doesn't have to be completely radical redesign. It depends on what design stage you're at. But there's always something that can be done in the design stages. And there's a lot of potential there as well. But a lot of designers are not that aware of what they can do. But just more generally, what can you do? One of the quick wins is concrete. Concrete and steel are two of the big hitters in buildings. They contribute the vast majority of the carbon footprint of most buildings. When you talk about civil engineering, they're even more significant. One of the main things, the quick wins that you can do, is a cost-effective measure, is to use in concrete mixtures, blast furnace slag or fly ash to replace some of the cement content. So reduce the amount of cement you need in the concrete mixture, because cement is very high embodied carbon per kilogram. And the implications of this are simply longer curing times and change in pigment. and there's a few other things as well. But there is a bit of resistance to using these, and that is one of the best ways of saving embodied carbon. Recycled materials, generally, reuse. Reuse is one of the best ways of saving. Designed for reuse, so if you can't reduce the embodied carbon of the stuff going into the building, you can try and design it to be recovered at the end of life. Dematerialization. Do you need as much material? Lightweighting, etc. Sometimes some odd things come out. When people look at embodied carbon and materials per kilogram, they'll note that aluminium and stainless steel are two of the higher embodied carbon factors per kilogram of the material, particularly aluminium. Per kilogram of aluminium, it's very high embodied carbon. But that's not a fair comparison, because you have to consider that it's got a lower density than, say, steel, and you have to consider that it's, for example, it's anti-corrosion. So it depends on the application that you're using it, because repainting, recoating is quite carbon intensive. It has a lot of other LCA impacts as well. So you have to assess based on the basis, but anti-corrosion metals, they don't require regular coating, and this can be a benefit not only to the environmental impacts, but also to the maintenance regime and the lifetime of that product. End of life. Unfortunately, end of life is very complicated, and you're talking about the future where you're making assumptions. But there are benefits from recovering, say, timber for energy incineration. Metals can be recovered for reuse or indeed for recycling benefits. General rule of thumb, doesn't always work, but general, use natural, minimally processed materials. And again, design. Design has huge potential for savings. Some of the recent projects we've done with designers and contractors in domestic sector, flooring for a normal house, instead of just a cast concrete flooring, a beam and block flooring, precast concrete, which is actually quite high carbon per kilogram compared to in situ concrete. A beam and block flooring with lightweight aggregate blocks was a better option. What Jane said before about considering the implications on operational carbon as well. For the aggregate block wallings, there was a very nice product that's made up of 80% PFA, pulverized fuel ash, which is a waste product from coal-fired electricity generation from Hanson, that has a higher embodied carbon than medium or heavyweight density blocks. But because it's lightweight, you get a better U value. So there's other things to consider as well. Now I'm going to give a few slides on the work that we did with the Sustainable Energy Authority of Ireland on an embodied energy and carbon project. We delivered this work with Davis Langdon recently. So the SEAI released an open tender to produce an embodied energy and carbon database for Irish construction. Now I can only give you a very brief overview of this project because it's currently going through a peer review process. So I can just I can't talk about the fine technical details, but we are allowed to talk about the what you can expect to see coming out of this project. So this was delivered at the end of last year and early this year, and the project was split into 5 phases. And this is just the start of the journey for the SEAI and indeed Ireland into the world of embodied carbon. Phase 1 was a standard literature review of LCA tool, embodied carbon standards, database and tools out there. It's becoming an increasingly clustered landscape, and it gets more confusing for clients to know which tools and standards to use. Bearing in mind this was done before any of the CEN TC 350, the real calculation methods and product standards came out. So the literature review was done before those standards came out, which are quite new and recent. Phase 2 was scoping more the design of the Irish assessment method. This is a calculation method to calculate embodied energy, embodied carbon for Irish materials, building products, and buildings. And then phase 3 was to actually deliver an embodied energy and carbon assessment method for construction materials. Phase 4 was to deliver an embodied energy and carbon database for Irish materials and construction products. And phase 5, an assessment method for calculating embodied carbon of building assemblies and elements. So it's not just about kilograms of concrete or steel or cement, but it's about actual real walls, roofs, floors, etc. So that's a bit of guidance around how to calculate that. I'm not going to talk about phase 1 and 2, they're just standard literature scoping studies. So phase 3 is a calculation method, how to calculate the embodied carbon for a material or a product. So rather than reinventing the wheel, because there are standards out there, and digressing too much from what's already been done, it builds upon existing standards. So it sets boundaries and offers, I would give you the boundary diagram, but that might change. But for example, it goes through the process of calculating a detailed product carbon footprint. Fortunately, you can't read this, but how do you calculate the product carbon footprint of this brick, or this timber panel, or this pane of glass? The process that you have to go through. Now, this is quite a technical document because there's quite a lot of fine details that you have to consider, some key issues that come up with calculating the embodied carbon of materials and products. These are things such as how do you allocate impacts? So a common problem is you have one energy source coming into, let's say there's a machine. The machine produces two different products, one energy source coming in, two products coming out. How do you divide one energy source into two different products? Do you do it based on the volume of products coming out, the mass of products coming out, the economic value of each product coming out? Depending which method you use, you get very different results. And that is one of the main issues in LCA and indeed embodied carbon assessment. Carbon storage for timber. This is also one of the main issues, and this is featured in the method as well. And generally ensuring the results are as fairly comparable as possible. So also one of the historic problems of LCA embodied carbon assessment is that the results just aren't comparable between two different studies because they're done to different assessment methods. They've made different methodological choices. One's not right, one's not wrong. They've just had very different approaches. So it's trying to ensure consistency and comparability to say that this brick manufacturer does an assessment of this product and this competing product done an assessment of the same method, and it's a robust, fair comparison. Phase 4 was to actually produce data on embodied carbon of Irish materials and products. We've actually collected some data for, where possible, for the production of Irish building materials, focusing on some of the main, there's an infinite number of materials out there, construction materials. So with the resource available, we had to concentrate on some of the main construction materials, brick, cement, concrete, timber, etc. There was a core of 7 main materials which we tailored the data for Ireland, and these materials capture the vast majority of impacts across most construction assets. This is the process that we've gone through to do that, which you won't be able to read again, but essentially we tried to collect data for Irish production, and actually there's excellent, I have to say there's excellent data in Ireland for some of the larger manufacturers because of the, I believe you've got regulations that companies have to produce annual environmental reports that go to the SCAI. It's available on their website, and that gives you what their energy consumption was, what their consumption of materials was, and what their output of the product was as well. Now, you can't always use that, but that's generally what we're looking for in embodied carbon assessment. Now, if the factory only makes one product, great. If they make 12 different products, then it becomes very difficult to use. But there's some very good data out there, and there's also other studies out there from the international market. Some materials are more of a local products, aggregates, cement, etc. You've got Irish production supply. You actually have Irish production of timber as well, but you export a lot of it abroad. It's not got the structural properties to use in construction. And then a lot more materials are more from an international market. A lot of the metals, etc., are imported. So adapting the life cycle assessment for steel for Ireland is not exactly appropriate. It's about importing the steel to Ireland because they're made all around the world. This is just one of the flow diagrams of the type of things you need to capture. This is just basic for, say, concrete. Now, concrete is a constituent mix of other materials. So you've got the cement, which we've calculated the Irish emissions factor for cement production. There's 4 big cement producers in Ireland. Aggregates, generally a local material. GGBS, water. These all go in. These all have different transport by different modes of road. And then batching. They've got to be batched. That consumes a bit of energy. And there's some mixing waste from the batching. Then it becomes ready-mixed concrete, which needs to be transported to site. So by scouring the literature and putting together the numbers for this, has produced an embodied carbon database for materials and indeed also for some products. So the difference between a material would be 1 kilogram of clay brick, but a product would be an actual brick of set dimensions that you'd use in an Irish house, or a concrete block of set dimensions, or a steel I-beam of a set profile. So that's phase 4, which will deliver some real Irish data from embodied carbon materials. Phase 5 is a calculation method for building elements. So to calculate the embodied carbon of walls, floors, roofs, etc., it's of particular interest to quantity surveyors or the whole building level. So go through the calculation process to do that, to add a bit more consistency to those type of assessments. To generally summarize, that's the outputs that can be expected. So there'll be mainly embodied carbon data, embodied carbon method for calculating materials and products. There'll be a database for construction materials and some construction products, and a calculation method for building elements and assemblies. Now, it has been tailored as much to Ireland as possible. It should be noted that the calculation method, or generally, this is a general comment I have, I firmly believe that calculating the embodied carbon of a product, material, etc. is a lot more complicated than doing a whole building. Maybe some other people disagree with me on that, but you've got to go into a lot more finer technical detail. And then if you're using a robust, consistent database of emissions factors for all the different materials that go into that building or product, the calculation for that whole building becomes a lot easier because you don't have to go into every fine technical detail because the database has already done it for you. It's not quite as simple as that, but for example, you've got a robust database, you know how many kilograms of bricks, concrete, steel, glass going into a building, you multiply out the quantities by the emissions factors, and that gives you embodied carbon, cradle to gate to make the building, you add in the transport, cradle to site, you use the same cradle to gate emissions factors for the maintenance of the buildings, how many times do you replace the clay tiles, etc. And it's just end of life. That's actually quite complicated. The initial outputs are undergoing a peer review process now, and it's just the start of the journey for the SAI. So this is a venture into the world of life cycle assessment and embodied carbon, which is, it does take you time to get head around this subject, and it will take industry a time to get their head around this subject as well. Now, I don't have time to go through the supply chain carbon slides, but the point here is it's about the mode of transport that you use to transport goods. So this graph here shows a higher carbon impact to transport 1 ton of goods 1 kilometre. So this is air transport on the left, shipping on the right, and the surprising thing here is transporting by a reasonably, not quite a small truck, but a rigid truck you see regularly on the road, 73 times more carbon intensive to transport 1 ton of goods 1 kilometre than shipping things in bulk, for example. So it's not just about the total journey distance, but it's about the modes and the journey distance for transporting goods. I have one final slide to leave you on, which considers the 3 pillars of sustainability, economic, social, and environmental. It's just a rhetorical question. So which of these is the more sustainable way of transporting people and goods? Is it an individual car, that almost everyone has an individual car, or underutilized? Or is it in fact a manky old overloaded truck that is crowded? Considering the full economic, environmental, social factors, it's not a simple answer, but it's just a rhetorical question that I think makes you think. Thank you.